All right, and welcome to week 15 of the semester. Okay, as you see from the announcement, quiz 45 to 50 will be due this Saturday. Yeah, once again, sorry about the many quizzes during these couple weeks because we're teaching routing. It's a distributed algorithm, distributed mechanism. So it's not always working in a synchronous way. Okay, so the complexity is a little bit higher. I would not say that the difficulty is higher, but the complexity is indeed a little bit higher. Okay, so we do need more quizzes to exercise you guys is to make sure that you pick it up. Okay. So today there will be 2 more quizzes. Tomorrow, 3 to 4 quizzes depending on how much time we have. Okay. And next Wednesday is the exam 3 day. All right. So the rules and the settings, the scope of the last exam, those will be announced in the exam 3 channel. Those who have clicked into the channel already, you will see that the date, exact time, and the exact scope as well there. All right, so everything will be the same as exam 1. The only thing that you might want to note is that exam 3, the length and the difficulty is probably about the same level as exam 2. Okay, and we'll again be cool about the cutoff time. Okay, yeah, so be careful about that. There's a penalty for late submissions. And what I can say is that what you guys did for exam 2, that is perfect. Okay, so you guys are all well in time. Okay, that is good. Let's keep doing the same thing for exam 3. All right. And given the experience with exam 2, you probably know that the exam is so long, everyone will be busy. Okay, you don't really benefit from asking others for solutions. Chances very high those are not exactly correct. So the best way to prepare for exam 3 is that you spend time. Okay, and as you are going through the quizzes we went through, going through the old exams, avoid looking at the solution and see if you can come up with the solution correctly from yourself. So that way you know that whether there's blind spot in how you think what Polly was asking or what the question is asking. Okay, so avoid looking at the answers and trying to work on it. That way usually works better, and it will show in the exam results. And of course, the Google form and the Google Meet session, those links will be available, I think, a day before the exam as well. So essentially, everything will be the same as exam 2 in a way. All right. And I see, hi Liangxin. All right. So that's those are the announcements today. And the first topic today is bad news travel slow. So if you recall, last week we ended talking about a quiz number 44, and we were talking about a scenario that looks a little bit more like this. Oops. So I meant to show you guys these. Okay, so this was the slide before we started doing quiz 44. You see that we have a graph here. It has 3 nodes, X, Y, Z. Link cost was originally 4, 50, and 1. And then suddenly the link between X, Y, the cost is increased from 4 to 60. Hey, this is bad news, right? Because, hey, the cost of traveling this link is much higher. So such a bad news, it's going to take a long time for distance vector to converge to the true route. That is why we call it bad news travel slow. And quiz 44 and coming up 45, 46 are trying to tell you that how slow it is. Okay, and on the slide here, you see that Polly is telling you the answer. It would take 44 iterations before distance vector will stabilize to the true route. Okay. So let's come back to quiz 44. How about that? Yeah, so this was quiz 44. So Polly has already shown you how to derive the big dx, the table for no x, and it looks like this. Okay, so for some reason, dx, the distance from x to y, distance from x to z, we quickly find what is the true route. So with the link between x, y, the link cost changing from 4 to 60. The best way to x is obviously x, z, y cos 51. Best way to z is x, z cos 50. Okay. But as you guys are working on the table for no y, you were surprised, right? You thought that the best way from y to x should be like, yz x 51 or y directly going to x cos 60. That's in fact many of you guys said at the first place, from y to x 60. But you know what? That's not how distance vector work. That's how human works. Okay, so let's review that video. Polly tries to illustrate exactly how you derive big dy, which is to calculate small d yx, small d yz. Okay, those two question marks. Let's review this. And coming up next is quiz 45. We'll actually go on iterating through such a change from link cost 4 to 60 between no x and y, and see if we get to stabilize to the true route after 44 iterations, meaning do we get to stabilize at t44. So we are now still at t0, right at the point the link cost is changed. Okay, so let's go through the video so that reminds you how Bellman-4 equations are calculated and applied to distance vector routing. So this video, once again, showing how you derive dy, big dy, for no y. dy. Okay, again, let me put up the solution first. So dyx, the first entry here, you thought, right, it should be 60, obviously, but this is as a human, you see the global topology, you know it's 60. But distance vector is actually what? Making decision based on local information, based on information provided by the neighbors. So let's be careful and then still walk through the Bellman-4 equation. Okay, so dyx, source being y, destination being x. Going through two neighbors, x and z. Link cost is link cost yx is 60, link cost yz is 1. So we have 60 here and 1 here. Now, going through neighbor x, what is the shortest distance to x? dxx, we'll have to look up the table, dxx, which is 0. Going through neighbor z here, what is the shortest distance from z to x? Z to x. That will be looking up the dz vector, okay, and going to x. So it's this guy here, 5. So we put 5 here. And you know what? Bellman-4 equation says comparing 60 to 6 wings. Okay, and that is actually going through no z. So y is going to pick. Okay, saying to go to x, let me send it to z first. And then z says, I know a way to x, which is, yeah, the old impression, right? This way. So you see the packet there is going to go y to z, z to y. But y is going to say that, hey, to go to x, you need to borrow z, okay, as the middle point. So that packet is going to loop around between y and z for a while. Interesting, isn't it? Yeah, this is actually a very interesting characteristic of distance vector. Okay, before the route actually converges, the packets could potentially be in a routing loop. So 6 here, again, is the new dyx. Okay, it's not quite yet the true, okay, dyx. Okay, so you see here,
even though y is capable of detecting, there's a link cost change right here. Okay, but y's routing decision, route calculation, is still based on the ODX and ODZ. Okay, and right at the link cost change, no y, okay, have not yet received the new DZ, new DX yet. So y is going to be using the ODZ and ODX. Therefore, you see, okay, the ODZ is telling y the shortest distance from z to x is 5 here. So we will be, in the short term, okay, under the false impression that this is the best route, y sent to z, okay, and z will somehow know away the cost is only 5 to x.
And therefore we get the 6 and 1 for dy. Now, quiz 45 is asking you, can you derive dz at time t1? Okay, so let me illustrate. So we just finished deriving the table for y at t0. Now, derive the table for z at t1. Because at t1, as t0 finish, as x at t0 finish calculating dx, we get 0, 50, 1, 50. So that vector will be distributed to the neighbors, including z. Y also finish recalculating dy, that is 6, 0, 1 at t0. That is different, right, from previous 4, 0, 1, and that will be distributed to the neighbors. And therefore, at t1, z will have dx 0, 51, 50 from no x. Z will have dy 601 from no y. Now, based on these vectors, dx and dy, calculate what new dz should be. So that is essentially calculating small d, zx, small d, zy. So the two question marks. All right, so this is going to take a while. Again, my suggestion is not to look at the solution first. Just don't look at the solution. Try to work on it yourself. That way you discover your own blind spot first. Okay, so that's allocate a good 10 minutes. Okay, that's each of us work on it. And for this quiz, you don't have to compete. Okay, anyone that provides the correct solution gets the point. So no bonus point for quick solution. And try to avoid giving me solution without really deriving it yourselves. You know that when it's exam time, you will have trouble deriving it this way. And what is the point of taking a course if all you care about is to get bonus, get points, instead of learning something? All right, good. So you have 10 minutes, okay? And Polly is just gonna wait for 10 minutes, okay, before we come back to look at your solutions. Okay, let's do that for a change. Okay, now, you don't have to be speedy for quiz 45. So for quiz 46. Yeah, find solutions. Try to exercise Bellman 4. So this is actually trying to prepare you for the exam. So use this time this way. That will save you some time next week preparing for the exam as well. Yeah, it does look like that the teams that are attending today have already uploaded the solutions. Okay, so I see that many teams did very well. Yeah, the solution is indeed 7-1. Okay, so 7 to go from z to x and 1 to go from z to y. And among all the solutions, I think Guan Yu did the best because Guan Yu spelled out all the elements in the Bellman-Ford equation, right? CZX, DXX, CZY, DYX, CZX, DXY, CZY, DYY. Okay. Good. So this way, I know for sure that Guan Yu will get the questions that's related to distance vector right in the exam. And I do see also team 10 and team 5, okay, actually takes this as input to y and this as input to x. Okay. Yeah, I think. So maybe I was not exactly clear. So what we are looking to calculate is this table of z at t1. Okay, so at this point in time, no x sends the new vector 0, 51, 50. No y sends also the new vector at the t0. So the new vector for y should be 601 here at z. So it will no longer be 045001500, such as what we had before T0. So those are the tables before we have the route change or link change. Okay, so T0 is right at the moment that you have a link change. According to the distance vector algorithm, when there's a link change, what do? We recompute the table based on the current distance vector table. All right. Okay, so hope that that address what's confusing team 10 and team 5. Very good. And I think Amelia gets it right as well. So is team 1. And so is team 3. All right, very good. Now, let's move on to the next quiz. You see, this is T1. Okay, so one iteration. And as you can see that, hey, it's going a little bit odd, right? Because Y's table was weird. Y's table was really weird. Yeah. Y's table was really weird because we do have, let's see, 601. And that gets propagated into Z. And as a result, Z has 710, right? That's once again weird because we know for sure as human beings, the best way from Z to X is what? Simply 50, right? So that's really odd. So let's keep on looking and see how much more odd the table can be. So quiz 46 here is asking, let's move on. Go to time T2. And can you tell me the table at Y? Okay, so that is this table here at Y. So in a way, Z's vector 710 at the next moment will be propagated. And as it reach node Y, we see the Z vector here will be changed to 710. Okay, so what will be dy then? Okay, so what are the values in the question marks? So once again, let's use 10 minutes time here and try to do the Bellman-4 equation yourself given dx and dz and calculate dy. It's 1:45. Let's go ahead and start and counting 10 minutes. right, so I guess you guys all pick it up. All right, so just so that it's very clear, let me play the video Polly has recorded deriving table for z at t1 and deriving the table for y at t2 and explain how come the whole process is going to take 44 iterations in order for y and z's table converge to the correct routes. So obviously 6 is not the true cause for z to go to y, right? Yeah. For z to go to x, sorry. Yeah, 6 is not the true cause for z to go to x. And 7 is not the true cause for z to go to x. And 8 here is not the true cause for y to go to x either. Okay, so x and y are having trouble finding the shortest path, the true shortest path to go to x for some reason. And that's going to go on for a while. Okay, so let's go through the video. And first is deriving the table of z at t1.
You should get a sense that it's going to take a while for these routes to converge to the shortest path. As to how long, yeah, let's try to walk through the scenario for a couple more iterations to see. So we'll develop the table, okay, for t1 and t2. Right? And at t1, z here can try to calculate dz because it now receives the distance vector of dx and dy coming from no x and no y correspondingly. And so dz here contains two entries, dzx and dzy. Now let's ignore the calculation of dzy as this one is very trivial and we know how to do Bellman-4 equation already. Okay. Let's go over, however, dzx carefully because this entry here is very interesting. So once again, okay, from source z to destination x, two possible neighbors of z, x and y. So first neighbor here, the link costs 50. Second neighbor here, link costs 1. So we have 50 and 1. And then the final destination is x, so we need to know the value of dxx. Final destination is x, so we need to know dyx. So for these two entries, we do table lookup because this is actually x's perspective. Okay, so this is what x has informed z. So what x has informed z is the dx. So in x vector, okay, to destination x, entry will be 0. In y vector, for destination x, entry value 6. So 50 compared to 7, 7 wings. And therefore, we update dz to 7, 1. Now, what's interesting is this. Z thought, okay, the shortest path to x is now what? 7. And the best neighbor is z. So z thought, okay, next hop to forward the packet, destination being x, should be y. But you see, y here thought, okay, the shortest distance to x is 6, and the next hop is z. Yeah, because z knows a way, okay, much earlier saying, oh, the shortest path to x is 5, and next hop is z. Okay, so you see we have actually looped it 1.5 times, okay, on link y and z trying to develop, okay, what is the true shortest path. If we continue on, okay, as z here finish calculating dz, this is going to go out and reach no y and no x. As a result, no y here can calculate dy again, provided the new dz. Okay.
All right. So that was calculating the dz. Now, there's also the video calculating dy at time 2 and discussing how many iterations before we really converge to the true route.
Let me bring up the result. dyx, this value here, is going to be 8. Let's look through it again. Okay, from y to x, y to destination x. Through neighbor x, neighbor z. Link cost 60, link cost 1. Link cost 60, link cost 1. dxx, 0. dzx, look up the table. Z's x, 7. 7 here. So, wow, we get A. What does that mean? Yeah, although we update the table for y so that it's 8, 0, 1. But you see, y here, well, actually believe firmly z is the best neighbor to forward the packet because z knows a way which takes only 7 dollars to go to x. And this is going to go on, in fact, because y here is going to announce dy also, to all the neighbors. And z is going to recalculate the dz. And guess what? And the next is going to be 9, 1, 0. And back to y, 10, 0, 1. Okay, all the way until when? Until z finally discovered that 50 is the true cost to x. So until, in dz, the value becomes 50, 1, 0. Okay. And how many iterations would that be? Yeah, came all the way from 7 to 50, that would be 43 iteration. Okay. And including the initial iteration, that would be what? 44 iteration. Okay. Until z discovered the true path. Next, then y will discover the true path. And then everyone converge to the shortest paths that are really true.
All right. And for solution to quiz 46, yeah, Team A's solution is perfect. Okay, it contains all the detail you see here. Yeah, the two options in Bellman-4 equation. Okay, and the exact values. So it's not just that it's detailed, but also very clearly presented. All right. And I think Team 14 is great, showing that, hey, if one is not careful, you see the first entry should come with, so every entry, in fact, right, should come with a link cost and then plus the shortest distance to the particular neighbor, right? So for neighbor y, then it will be then the shortest distance from y to, I think this is calculating destination being x. Okay, so this should be then y to x, and this should be d. Okay, so dyx here. Okay, so you see that if one is not careful, then you ended up writing terms that are not exactly what the Bellman-Ford equation is asking for. Okay, so these are the places you might ended up making tiny little mistakes, but eventually the answer might not be right. All right, good. And you know what? That takes us to the next topic. How do we address this issue that in distance vector, whenever it's bad news, then it travels slow. It takes a lot of iterations to converge, and during this time, packets will just loop around until the true paths are discovered. So that technique is called the Poisson reverse.
The problem here is, right after link cost change, when y is trying to recompute, the best route to x to z, particularly to x, Bellman-Ford algorithm says y needs to try, calculating the total cost through neighbor x, neighbor z. To neighbor x, best distance from x to x is 0, trivial, but the link cost is suddenly 60, just to get from y to x. So together, total cost 60. Not very good. But the other neighbor here, z, was still under the perception that the best route is this and the cost is 5. And y here says the link cost between y to z is only 1. So y is going to insist, why don't I send packet here? Z is going to send the packet on behalf of me and taking only cost of 5 to reach x. Y does not know. Z is actually under the perception that this is the best route to go to x. So z is going to send the packet back to y, and y is going to send it back to z. Z is going to send it back to y. So this packet here is going to loop for a while, until y discover, the real shortest path to x. So z here, being still under the impression that the best route is the one before the link change, needs to know about the link change. Poisson reverse is working this way. This is to help preventing bad news travel slow. In Poisson reverse, y and x, the two ends of a bad link, is going to tell their neighbors that, oh, all your routes, okay, all your shortest path routes to the other node along the link needs to be changed to infinite, okay? That way it prevents, okay, y selecting z, okay, as the shortest distance to x. Let's use the same example to illustrate how Poisson reverse works. So taking one step back, before we have the link cost change. Now z here will discover a shortest path to x this way, z, y, x. So shortest distance from z to x is 5, and the next hop router is y. Now, link xy here, the cost changes from 4 to 16. X, Y, these two routers being connected to the link will be able to discover the link cost change, but Z here being farther away couldn't. As a result, Z will be telling Y, hey, this is the shortest distance from me to X. And that's why in quiz 35, when we're calculating the shortest distance from Y to X, we ended up having this, right? Because Z is a neighbor of Y, link cost is only 1, and Y is being told by Z, 5 is the shortest distance to x, therefore we do 1 plus 5, and we ended up having 6 here, okay, a funny value for the shortest distance from y to x, which we see from the network after link cost change, there's no way this is the right value. So to avoid, okay, having confusion such as this, we should stop, okay, z from keep telling y this is the shortest distance. So z tells y instead, okay, the distance to x is not 5, instead being infinite. Okay. And that is what you're seeing here. Distance from z to x at y's table now being infinite. And how do we achieve that? It's not that hard. So if this is the link having a link cost change, we ask the node right adjacent to the link to try to probe the neighbors. If this node here discover there's a route coming from the neighbor and using itself as the next hop. Okay. So if y here discover in one of the neighbor, okay, and this neighbor is using itself, okay, as the next hop to a destination, okay, set this entry here in y's table to infinite. With now dzx being changed to infinite, the way we calculate dy in iteration t0 will be different. Okay, so dyx particularly is the entry with different value. It was previously 6. Okay, but now let's see how it's going to look like from y to x. Okay, there are two possible neighbors, x and z. Link cost to the first neighbor, link cost to the second neighbor, 60 and 1. And then from first neighbor x to destination x, dxx. From second neighbor z to the destination x, dzx, dxx, dzx. Set up table, xx, 0, zx, infinite. So 0 here, infinite here. Comparing the two, yeah, 60 better. Okay, therefore, shortest distance from y to x is now, yeah, the direct link, link xy. And then the next point in time in T1, z here is going to receive the distance vector from x and y, and this time dyx is 60. That's going to change, yeah, the result of the dzx, this entry here. So let's see, dzx. From z to x through two neighbors, link cost being 50 and 1, 50 and 1. dxx and dyx, dxx, dyx, so xx value 0, yx value 60. So 0 here, 60 here. So comparing 50 to 61, 50 wins. And you see here, from z to x, yeah, we're taking just this link, zx, as a direct path to destination x. Quite different, isn't it? So we update dz, and dz is going to go to the neighboring nodes. Okay, and so y here, recalculating dy again, the dyx is going to be different as well. Okay, so dyx, okay, two neighboring nodes, 60 and 1 are the link cost. the XX 0, the ZX, ZX, entry value being 50. So 51 compared to 60, 51 wins. So to go from Y to X, now the shortest distance is, this path. And in fact, at this point in time, so let's update the distance vector for Y. At this point in time, the network converge to the true shortest path. And it takes only what? 2 iterations, as opposed to 44 previously.
All right, so that was the fix to distance vectors issue with the link cost being bad, traveling really slow. And next video is just to summarize routing algorithms. We've heard link state routing, and today and much of last Wednesday, distance vector. So here's a comparison and to sum everything up.
Now with both routing algorithms introduced, let's compare the two algorithms. LS here stands for link state. DV is the distance vector. Let's compare the message complexity first. If you recall, in link state, each router there needs to generate this link state report, and it gets broadcasted throughout the network. So each of these link state reports is going to travel all the links, and there are E of them, and there are N nodes. Each will be generating these link state reports. Therefore, overall cost N E. In the worst case, in case the network is very well connected, the E here is about the scale of N squared. So overall, the cost can go as high as N cube. So link state message complexity, not good at all. Distance vector, on the other hand, the message exchanges between the local neighbors. Right? And as you see in one of the examples earlier, as soon as the route converges to the shortest, no more distance vector messages being passed further. So there seems to be some opportunities for some node to stop message passing early. So in terms of message complexity, DV is slightly better. Now, the second metric, the speed of convergence, the time it takes to converge to the shortest path. In link state, it runs the Dijkstra algorithm, which we know the time complexity being N squared. There's some optimizations one can apply that takes you to N log N time, even better. So link state seems to be okay, except that we need to be careful about setting the link cost. Try not to use the traffic going on the link right now and changing it dynamically. On the other hand, in distance vector, well, the convergence time varies. In some of the earlier examples we see, in a 2-hop network, it takes only 2 cycles to converge. So if you think about it, the convergence time for a network is pretty much in the scale of the diameter of the network. But that is actually in the ideal situation. What if we have bad news that we need to propagate through the network? Then we could run into the count to infinity problem. And during the phase of counting to infinity, the packets will be looping from router to router. So in distance vector, the convergence time is a little bit hard to predict. It really depends on the situation. On the other hand, link state, very predictable. I would say in terms of predictability, link state wins over distance vector. But under normal situation, distance vector's convergence time, is indeed the diameter of the network. There's not many hops. Even for a large network, the diameter might not be so long either. The third matrix to compare, the robustness. What if a router is malfunctioning and reporting the wrong link costs? Things like that. In link state routing, during the phase the router is malfunctioning, the neighboring nodes will be advertising the wrong link state reports. And each router will be calculating the shortest distance based on the wrong link state report. But once the malfunctioning goes away, link state report will be corrected, and quickly each router will be calculating the shortest path based on the correct link state report. So the time you expect the network to recover from the router malfunctioning is expectable in link state. In distance vector, however, if a router is malfunctioning and reporting, for example, a short link cost to a particular neighbor, the node can actually falsely reporting Okay, the shortest path to a particular destination being shorter than expected. So these incorrect paths gets advertised and propagated out. And the neighbors of these nodes is going to take it and potentially include that in the shortest path and updating the DB and then pass the incorrect information further. Yeah, each node's table is going to be used by the other. Each node's distance vector is going to be used by others. Yeah, this error is going to propagate out throughout the network, and it might take a long time, yeah, for the network to recover to the correct cost. Taking a long time and not very predictable. So in terms of robustness, yeah, link state here is still winning by a head, by a neck.
All right. So do you prefer link state routing or distance vector routing? All right. Feel free to let me know and type it up on YouTube chat. And with that said, that's all for today. Tomorrow is going to be the last lecture this semester. Okay, so we'll be wrapping up everything tomorrow. There will not be lecture next Tuesday. Okay. Tomorrow we still have something to talk about. For example, the exact routing protocol running on the internet that's based on the link state routing, and the exact protocol running on the internet that's based on the distance vector routing. So there's one protocol for each of the routing algorithms. And we'll learn about these protocols tomorrow. With that said, bye. Now go out and, well, actually, I'm not quite sure it's appropriate to go out these days. So, hey, go on and try to tune into the next lectures that are online. Okay, good. Bye. Yeah, bye. Okay, and Polly is gonna end the stream.